Good afternoon, everyone. Myself Bhavish. I am the session host of today's Brahmagupta Colloquium Seminar. It's my pleasure to introduce today's speaker, Dr. R. Vijayaraghavan, Associate Professor at the Tata Institute of Fundamental Research, Mumbai. His research lies in the forefront of quantum measurement and control, focusing on superconducting quantum circuits, a key platform in the development of quantum computing. Dr. Vijayaraghavan completed his doctoral research at Yale University under Professor Michel Devoret, who is one of the Nobel Prize winners in the physics this year, along with John Clark and the John Martini. So they pioneer experiments on quantum tunneling and energy quantization in macroscopic electrical circuits using Josephson junction have paved the way for realistic quantum bits or qubits in superconducting circuits. Following his PhD, Dr. Vijayaraghavan carried out postdoctoral work at UC Berkeley, continuing his investigation on superconducting qubits. He now leads a quantum measurement and control laboratory at TIFR, where he heads several projects aimed at building small to medium scale quantum processors with support from major Indian funding agencies such as LEAD PI for the National Quantum Mission, Superconducting Quantum Computing Initiatives. In today's talk, he will discuss these seminal experiments and share his personal experiences working closely with Professor Devoret, giving us unique insights into the origin and the future of superconducting quantum circuit. Please join me in welcoming Dr. Vijayaraghavan.
Thank you for the kind introduction, and thank you, Prabha and others, for inviting me. As she keeps reminding me, this visit has been long pending. So as Bhavesh said, I hope to explain to you this experiment which has been recognized with the Nobel Prize in Physics in 2025. The citation reads, for the discovery of, I hope to explain these things to you in somewhat more detail than you might be expecting. I was not only lucky to do my PhD work with Professor Devoret, but during my postdoctoral days in Berkeley, I closely collaborated with Professor John Clark, my postdoc advisor, and John had a shared student. So it was actually my first project as a postdoc, where we worked with John Clark, and also collaborated with John Martinez on some of the superconducting amplifiers related work. And finally, not only that, during my PhD days, I have done this exact experiment in a different context. So I know a little too much about this experiment. So you're going to have to learn all of that, but I hope I'll keep it in a simple enough way that you can understand why this experiment was important, what was really challenging, and how they actually were able to do it, and of course the implications of that experiment in today's research and technology platform. So I'll start at the beginning. We have to set some basic ideas straight in quantum mechanics. I mean, this is mostly a physics audience, I suppose, but yet I just wanted to set a few concepts so that we know what we are talking about. So starting from the Bohr model, which we learn often in high school, where we define the atomic structure as an electron orbiting around the nucleus in these well-defined orbits. We of course now know this is not an accurate picture, but one property which was already mentioned in this model is the fact that even though there are these well-defined orbits, there are only certain of those. The fact that you cannot have orbits having arbitrary radius or arbitrary energy was already mentioned in the Bohr model. So this is one of the things mentioned in the citation about energy quantization. So Bohr model already had this idea that electrons can only orbit around the nucleus at certain energies. Now, of course, later on Schrödinger came in and introduced his wave function, and then we understand that we can no longer talk about such well-defined orbits. We have wave functions which then give rise to probability distributions of where the electron can be found around the nucleus depending on its energy and depending on the rest of other parameters. So these are some of these funky shapes you get from Schrödinger's equation, and of course he won the Nobel Prize for this in 1933. So using this idea, I modify this picture slightly and make these orbitals a little bit fuzzy just for the convenience of discussion and being slightly more accurate that we don't know where exactly the electron is. Once I do that, I can now label these orbitals with these ket vectors, which are like wave functions. And because these are solutions to Schrodinger's wave equation, which is a linear equation, the math tells us that if you have these as possible solutions, then the system can also be prepared in states like these, which are combinations of these solutions. Right? So you already went from a mind-boggling idea that we don't know where the electron is in a particular energy orbital. Now you can put these systems in these so-called superposition states where you don't even know what the energy is. At least that's the way we try to describe it in plain language, that the electron is in both this orbit and that orbit at the same time, or it has this energy and that energy at the same time, until you measure. Now, this aspect of quantum superposition is not actually the main topic of the talk today. I will briefly come back to that because these initial experiments led to these ideas being now every day. We do these kind of experiments every day and create such states in our lab all the time. But there is this other property, which is quantum tunneling, which is very important, and that's actually the main experimental result. And very simply put, this idea that in the classical world, if you have a particle approaching some kind of a potential barrier, and if the energy is not high enough, this particle will either stop at the barrier or will be reflected back, because it doesn't have energy to go over the barrier. But if you now apply the principles of quantum physics, the very same problem, say an electron approaching a barrier, now the electron is defined by some wave function which has a spatial extent. The equations tell us that when it approaches the barrier, there is a finite probable value on the other side of the tunnel barrier. And that translates to the idea that there is a finite probability that the electron can actually be found on the other side of the barrier, or in general can actually pass through the barrier, even if it doesn't have an energy to overcome the barrier, right? So there is a non-zero chance that the electron tunnels through this barrier. Of course, this is a probabilistic process, but this is allowed in the quantum world. This, of course, had many examples, radioactive decay and nuclear fusion, where these nucleons have to overcome various potential barriers in order to either separate or to fuse, but also for instruments like the scanning tunneling microscope, where you bring a tip very close to the surface you are trying to image, and then if you are close enough, then electrons can actually tunnel through this gap, and the current tells you something about the property of the surface, and you can use that to image surfaces. And similarly, another device, which is actually the main actor in today's talk and this experiment, is a tunnel junction, where here I have shown this as two metallic electrodes separated by a very thin insulator. So you can think of this as a gap or a non-conducting material, so it acts like a barrier. You wouldn't expect current to flow through an insulating material, but if it is thin enough, then electrons can actually tunnel through this barrier, and this is called a tunnel junction. And these are routinely made and tested. So the electrons can tunnel across the small gap in the STM or in a tunnel junction where you have two metals separated by a very thin insulating barrier. But till now, we have only been talking about microscopic quantities like atoms and electrons, right? The Nobel Prize talks about this idea of quantum effects in macroscopic systems, right? So what about bigger objects? And this was something which troubled people a lot in the early days of quantum mechanics. And a simple argument goes, well, atoms and electrons make up everything. They seem to show these strange properties. Why don't we see those in objects which are composed of those electrons and atoms, right? So obviously we never see something like this happen in daily life, where a person banging their jumping towards or like approaching a wall magically appears on the other side. Of course, this happens in Harry Potter, if you know what I'm talking about. So this question that actually bothered the founders of quantum mechanics, and in fact, Erwin Schrödinger invoked this idea of Schrödinger's cat, this thought experiment, to actually explain the absurdity of this idea, right? So he says that this experiment illustrates the absurdity of applying quantum theory to macroscopic objects, as it leads to the illogical conclusion that a cat could be both dead and alive until its box is opened and observed, right? So all of you, I'm sure, are familiar, but just to remind you, the idea is that there is a quantum process which is probabilistic, it's a radioactive decay. So you don't know when exactly it would decay or not, and that decay can trigger a mechanism which can kill the cat. So if all of this is enclosed in a box, then you don't know whether the particle has decayed or not, so you can say that it is both decayed and not decayed, and hence, as a consequence, the cat is both dead and alive. Now, in the modern understanding of quantum decoherence and everything, we have a good explanation of why this is not the correct way to think about it, but this was something which clearly bothered people at that time, and there was an obvious question is, how large can a system be and still show quantum effects? Right? This is still sort of an unanswered question. There is no magic number, and there are lots of caveats when you answer this question. So people were trying to construct experiments where one could try and observe some of these unique properties which quantum mechanics gave rise to, namely in this case tunneling and energy quantization, whether it could be observed for some quantity which is not an atom or an electron, or say a photon, as for that matter. Right. So that's the main question and the main topic here. So here enters the main element which is used in this experiment, which is called the Josephson junction. And you've seen this picture just a few slides ago, with the only small modification that I've now labeled these metal electrodes with S, which means that these are metals which become superconducting. Okay. So these are superconducting metals separated by a thin insulating barrier. So now, instead of just electrons tunneling across the insulating barrier, we now talk about Cooper pairs, which happens in superconductivity, that electrons pair up and then form this condensate, and they tunnel through this barrier and can generate a current. What Brian Josephson did was he analyzed this system. Oh, by the way, this is how one of them actually looks like. What you are seeing is a thin film of aluminum and another thin film of aluminum, one on top of each other. So unlike the picture where I show these things on the side, in reality most of these tunnel junctions are made with one layer on top of another with a very thin layer of oxide. In this case, aluminum, aluminum oxide, aluminum as the tunnel junction. So Brian Josephson analyzed this circuit in terms of some of its parameters. So two of the important parameters are these numbers written here. I'll first start with Cj. Since this is two metals separated by a thin layer, it looks like a capacitor. It looks like a parallel plate capacitor, right? So this circuit element will have a capacitance which is just going to be driven by the dimensions of this device, and that is given the symbol Cj, so J for junction. There is this other quantity I naught, which I'll explain just in a second, and there is this quantity called the phase across the junction, and this will be the most important entity here, and I will explain that as we go through this slide. So Brian Josephson analyzed this circuit and he wrote down these relationships called the Josephson relations. The first one is for a current through this device is equal to this quantity called I naught, which is called critical current, that it's proportional to this constant times the sine of this phase difference delta, right? The important thing to remember here is that this current is called a supercurrent, which means that as long as this current is smaller than the critical current, you can pass a current through this device without developing any voltage across it. That's what you would expect if this was just a solid piece of superconductor, right? That's the very definition. Superconductor does not have any resistance. So if I pass a current through it, I'm not going to develop any voltage across it. The non-trivial or the surprising thing here is that despite there being an insulating barrier in between, you get a current flowing through it. That happens even when these electrodes are normal or normal metal. But in the case of superconductor, you can pass a current and not get any voltage across it. So it's a supercurrent as long as this current is smaller than this maximum value I naught, and that I naught, called the critical current, also depends on the dimensions of this. So you can control that by the design of the Josephson junction itself. Okay. He also wrote down a second relationship which is about the voltage and which corroborates the previous idea that the voltage is proportional to the rate of change of this phase, and there is a proportionality constant h bar over 2e, which is often called the reduced flux quantum. So if you now look at this idea that if I is constant and less than I naught, you will have a solution for sine of delta and hence delta, and if delta is constant, the rate of change of delta is 0 and voltage is 0. Right? So for a DC current which is smaller than I naught, you have 0 voltage. The second equation confirms it. But I can decide to pass an alternating current, still ensuring that the magnitude of that current is less than I naught. In that case, I will develop a voltage, but the voltage will be proportional to the rate of change. So if the current is like a sine, the voltage is going to be like a cosine, right? Which means the current and the voltages are 90 degrees phase shifted with respect to each other. You have come across this when you study reactive elements like inductors and capacitors. Exactly the same thing happens, which means that even though there is a voltage, you don't dissipate any power because current and voltage are 90 degree out of phase. So this superconducting nature, the fact that you can pass a current without any dissipation, works both for DC and AC currents as long as you are less than the critical current. Okay. Now about this phase, right? The modern definition of the phase is to actually invert this equation and say that, well, this phase is the time integral of the voltage across a Josephson junction. This is how we typically define it. But there are a few other ways of understanding this. One is related to the fact that you have these two superconductors, and these superconductors, the superconducting state itself is defined by a global wave function, which is sort of a collective property of all the Cooper pairs in that condensate which forms the superconductor. And because there is an insulating barrier in between, the phase of that superconducting wave function on this side and that side can differ, and that's this phase difference delta. So as you apply a current, the phases twist with respect to each other till a maximum current that can be supported, and after that this no longer behaves like a superconducting element offering 0 voltage. So this is the second way of thinking about it. But there is a more electrical engineering way of thinking about this phase as well. If you look at this quantity voltage being proportional to the rate of change, we have seen this before, right? Faraday's law. Voltage is proportional to the rate of change of flux, right? Typically when we talk about inductive elements. So you can think of this phi naught into delta as sort of as a magnetic flux, if you like. That's another way of thinking about it. Okay. So that's basically what defines the property of this Josephson junction in terms of its electrical properties, and Brian Josephson wrote this down and won the Nobel Prize in 1973 for this invention. Okay. Because of these properties, there is an associated quantity which emerges. This Josephson junction actually behaves from this relationship. You can show that it electrically looks like an inductor. And I already told you that there is always a capacitor associated with the structure. So it's a Josephson junction which is represented by the symbol X. So you can think of this as an inductor in parallel with a capacitor. This is your famous LC circuit, which we often do experiments in our undergraduate labs. It has a natural frequency of oscillation given by 1 over square root of LC. And that L, this is the frequency, what we call as frequency of small oscillations. This L is actually nonlinear because it depends on the amount of current that is flowing through the junction. Okay, so that's an important thing to remember, that the Josephson junction behaves like a nonlinear inductor. So what is macroscopic here? Okay, so here's the full circuit. I have my junction, a capacitor. I have now added explicitly a current source for biasing it, and I have shown that the current source has some source resistance with it as well, and that has consequences for the dynamics of this thing. And this circuit, its dynamics can be understood by the dynamics of a particle, which we often call as the phase particle, which is sitting inside a cosine potential. Okay. Where does this cosine potential come from? It comes from that fact that the current is proportional to sine of delta. In this case, that current is like a restoring force. Okay, so do you remember any other physical system where the restoring force is proportional to the sine of an angle? A pendulum, exactly, right? So the pendulum's motion can be described as the motion of this theta in a cosine potential. So that's what it's going on here. This pendulum analog actually is exact for the case of the Josephson junction. If you write down the equations, it's exactly the same of that of a pendulum. But it also gives an intuitive picture of what do I mean by a macroscopic degree of freedom, right? This Josephson phase actually comes from a collective property of all the Cooper pairs in the superconducting condensate. If I think about the pendulum, in order to describe its dynamics, I only need to understand how theta varies with time, right? That's how we typically do it. But I can do it in a more complicated way by defining the position and momenta of every atom in this, which makes up this pendulum, right? That will also give you a correct result, but that's crazy. You don't need to do that. Because what we are interested in is the collective motion of all the atoms which are forming that pendulum, and they are moving together, and you have theta emerge as a collective degree of freedom. It is exactly in the same sense that the Josephson phase is a collective degree of freedom which involves the collective coherent motion of all the Cooper pairs in the superconducting condensate. So it's no longer one electron, it's millions of electrons, and hence it's macroscopic, right? It is in that context that we can interpret this degree of freedom. So essentially we are studying the dynamics of a pendulum but in an electrical sort of form, and the relevant degree of freedom is now no longer representing a microscopic degree of freedom. For the experts, I just want to add 2 points here. The superconducting state, itself is considered a macroscopic phase because of all the electrons and working together in a single representing their wave function as a coherent entity. And in fact, that property is connected with the Josephson phase also being a macroscopic entity. But you also have to remember now in the context of tunneling that every time there is a current flowing through this junction, Cooper pairs are constantly tunneling across the barrier, right? But those are the tunneling events of single Cooper pairs. It's 2 electrons, so it's still microscopic. So it's not that tunneling we are talking about. You will see what tunneling I'm going to talk about, which is connected to the degree of freedom theta in just a few slides. Okay. By the way, feel free to stop and ask questions if there are anything here. So now we come to the actual experiment. I will walk you through it, so don't worry about the complicated looking graphs. So again, the circuit is here. This is what is called as an IV curve. So current on the y-axis and voltage on the x-axis. So you start at 0, 0, so 0 current, 0 voltage, and you slowly increase the current. But initially, the Josephson junction offers no voltage as you increase the current till you reach the critical current here. At this point, a finite voltage develops, and if you increase the further current, you get a linear IV curve, which is representative of a resistor, right? Ohm's law, V equals IR. So out here, the Josephson junction looks like a resistor. Out here, it looks like a superconducting element. So you increase the current, then you get a finite voltage, and then when you retrace it back, I'm not going to go into the details, but because of the dynamics of the system, the retrapping back to the superconducting state happens in a very complicated fashion, and then you get a symmetric response on the negative side. So if you make the voltage current negative, no voltage, and then shifts to finite voltage, and then back here. So you actually get this hysteresis kind of loop. This depends on the details of the capacitance and the resistors and things like that, but in general, this is what is going on. So it's this transition from being at the 0 voltage to the finite voltage is this transition we are interested in. Okay. So just to give them names, we call the situation where the current is less than the critical current, the superconducting or the 0 voltage state, and if the current is greater than the critical current, you get into the normal state or the finite voltage state. To visualize this, you can actually consider what happens to the potential as we increase the bias current slowly as a function of time. Right now, because this current is now a static term, at every instant of time it's a static value, you can sort of rewrite the equations in such a way that now you can absorb that term in the potential, and then it looks like your cosine potential, which is a periodic potential and initially was flat, slowly starts to tilt down. So this is finite current, larger current, current equal to the critical current, and current greater than the critical current, right? Now the thing to notice here and pay careful attention is that as long as the current is smaller than the critical current, there is a little barrier in front which keeps this particle stuck in that state. And if it is stuck here, phase is constant, voltage is 0. If it jumps out of this, then basically it runs down and delta changes with time in a continuous fashion, and you get a finite voltage. Right? So this is a way to visualize what's going on in this situation when you are slowly increasing the current and you approach the critical current of this junction. Okay. So experimentally, you do this and you measure voltage as a function of time, and what you actually get is something like this. So voltage is 0 for some time, and then boom, the voltage increases to a certain value. Okay. Now if you repeat this experiment, you will see something a little odd. Next time, that voltage may not jump exactly at the same time, because remember the time here is connected to the amount of current that is present. If you do it again, you will actually see it at some other time and some other time. So this actually is a stochastic process, which seems contrary to what I have explained till now, because obviously the current can only exceed the critical current at a particular time if this rate is fixed. Okay? The reason this happens is that even before you reach the critical current, that is the point where this barrier vanishes, you can actually be kicked out of this stable state or metastable state, and then once you are kicked out, there's nothing to sort of stop you. The system gets enough momentum that it just runs down the hill and switches into the voltage state. The reason that happens is that there is always fluctuations which causes this phase particle to sort of move around here. What causes these fluctuations? It's the noise in the setup, which in the ideal case can be thought of as just the Johnson noise of this resistive element here, right? So some of you have studied about noise of the resistor. You can actually now model this as an ideal noiseless resistor, but add an extra term, which is a noise term in the current. So a resistor behaves like a noisy current source or a voltage source. And the intensity of that noise is given by the temperature at which the resistor is, and of course the value of the resistor itself. So in these experiments, one basically is feeling the temperature as a fluctuating current, which then, if the current is fluctuating, that means if you look at I is I naught sine delta, the phase is going to fluctuate. So the particle which is sitting at the bottom of this well is not stationary. It's going to be moving around randomly, and then occasionally it could make a motion which is large enough that it jumps out of the well. The probability of that happening depends on the amount of noise and hence connected to the temperature at which the experiment is done. So one can write down a rate of escape. So how frequently will such a system escape out of a metastable state like this? And you get this famous Arrhenius law. If there are chemists in the audience, this is very common, but this is also there a lot in physics. You get an exponential term which goes as minus delta U, which is the height of the barrier, divided by the temperature in energy units, right, kBT. So which means that larger the barrier or smaller the temperature, the smaller the probability to escape, and vice versa. Smaller the barrier or larger the temperature, the larger the rate at which you can escape out of this. And the prefactor here, this quantity omega p, is actually exactly that frequency of small oscillation which is present there. Okay, so this is going to be important to remember because this is part of the control experiment they did. So this is sort of often called as the attempt frequency. You can sort of imagine this as how often the phase particle is bumping against the barrier and trying to make an escape for it, right? Because that's a natural frequency with which it's going to be moving around on top of the noisy motion it is. So that is if I look at the noise spectrum, it will be peaked at omega p. Okay, so that's what's happening here. Because this electrical system is extremely well defined from the Josephson relationship, I can calculate exactly what the height of this barrier is. Okay, so don't worry about the details of the equation, just the fact that this can be calculated exactly. Given the critical current, given the bias current, you know exactly how high this barrier is. Okay, and then you can take this equation, you take the log and you do some renormalization here, and if you plot this quantity on the left hand side, there is a constant here which has a temperature in it. I'll come to that in just a second. But there is this term that this escape rate or inverse of escape rate goes as 1 minus I over I naught. So it's a straight line. If you plot this quantity versus IDC, you get a straight line which has an intercept at I naught, and its slope is inversely proportional to the temperature. So this is what the experiment they did. They measure this escape rate at different bias currents and make a plot of this quantity, which should give you a nice straight line, and you can extract two quantities from this. The critical current, which basically gives you a way to ensure that your experiment is being done correctly because it should match what you predicted. And it also gives this quantity which I have called escape temperature. Okay. The reason I have called this escape temperature is that what we are saying now is that I am measuring the probability of these escape events to happen. I am turning that into an intensity of noise and then turning that into an effective temperature, because I am saying that all my noise should come from the noise due to the fact that it is operating at a finite temperature. And this is an experimentally determined quantity. If everything works well, this escape temperature should be exactly equal to the temperature at which the experiment is being done. Okay. So that's what they do next. So you collect this data, you do these experiments over and over again, and then you make this graph, this straight line plots, and this is now data from one of the papers which you can find, which gives this experimental results here. So just focus your attention on the bottom part. You see there's this little discontinuity there, so ignore the top part and look at these. These are experiments done at different temperatures, starting from 400 millikelvin going down to lower and lower temperatures. So you observe that, and so remember that these are statistical events, so you don't have points at all currents. So what you observe is that when the temperature is high, most of the events happen at a lower current, and as you go to lower and lower temperature, most of the events happen at a higher bias current. Why? It's because of the Arrhenius law. When the temperature is smaller, it cannot escape till you make the barrier small enough that the probability of escape becomes high. So that's why you have to go to higher currents for it to switch in order at low temperatures, and it switches and also the distributions are broader here, right? And you also don't see counts after for larger currents as well. That's because at high temperatures, even before you reach the critical current, you would always have encountered escape event, and hence you will never measure a switching event close to the critical current or at the critical current ever. But all of these graphs, they all ultimately, if you now fit them with a straight line, and that's what these extrapolations are, they all intersect at one point which exactly should be the critical current of this device. So by doing these experiments at different temperature, you get data like this. It also confirms that all of the points, the critical current is basically the same. Of course, this is within experimental error, and you see the slopes are also changing, which means from this I can extract. So the slope becomes larger at lower temperature, which is what you expect. For small t, the slope is going to be larger because this is proportional to 1 over t to the power 2 threes. Okay. Now is the main part of the result. This is the experiment we have been discussing. Now when you are close to the point where there is a small barrier, we are so far been imagining that this fluctuation is going to cause the system to go over the barrier. Basically the noise gives that extra energy for it to overcome the barrier. This is the conventional classical process. But if I make the temperature small enough that this probability becomes very, very small, and now I want to say that, well, if this was a quantum system and the phase was a quantum degree of freedom, then I should also have a probability of tunneling through this barrier. And if that happens, the net result is the same. I'm going to escape out of this barrier, and I'm going to run down the hill, and I'll switch into the voltage state. So from this experimental voltage curves, there is no way to know whether an escape event happened because of activation over the barrier or tunneling through the barrier. So how do you distinguish these two possibilities, right? You do that by looking at the temperature dependence, because as you lower the temperature, the probability of escaping will keep going down, and at some point the tunneling process will take over, and then that does not depend on temperature, at least not very strongly. There are some corrections in the full theory. So what you would see is that the probability of escape as inferred from this quantity we call escape temperature will slowly come down with physical temperature and then stop. This is a data of that escape temperature versus bath temperature. This is not from the Nobel Prize winning work. This is from data which I took 20 years after the Nobel Prize winning work during my PhD days, and you see that effect which I was talking about. Escape temperature follows linearly, it doesn't fit exactly, but it's good enough. And then it saturates here. Okay. Now, if you showed this data to any reviewer, the first thing they will ask is, how do you know this saturation is due to some physics? Right? The most simple explanation is you have extra noise in your system. So if you have extra noise, let's say there was always some fixed amount of noise. Initially, temperature noise was much higher, so your experiment followed that temperature. And once the temperature crosses, the noise from the temperature crosses the extra noise you have in your experiment, you're going to see that noise, and that will be constant, right? So there is no way to, by looking at this data and say, hey, it looks like tunneling, right? In fact, in this case, it's not tunneling, it is extra noise, because we can calculate this quantity, which is plotted here as T star from the theory, which tells us at which temperature this effect will cross over, right? And that's given by this formula h bar omega over 7.2 k Boltzmann. This can be calculated exactly from the tunneling theory of that shape of the potential. So if you have temperature greater than T star, you see the escape temperature following linearly with bath temperature, and once T is below T star, the rate becomes constant because of tunneling, and that then can be interpreted as macroscopic quantum tunneling. That crossover temperature is shown here in this lower dashed line at 5 millikelvin, but in this experiment, the saturation happens higher. Okay. So this is due to extra noise. Yes?
This also puts stringent requirements on temperature measurement at such low temperatures?
Yes, but temperature measurements at these temperature ranges are now fairly standard. You can get accuracies of 1 millikelvin. That technology has not changed for decades. You were able to measure. Basically, the temperatures are measured by measuring the resistance of a special resistor. In this case, ruthenium oxide. More sophisticated ways involve actually looking at some radioactive decay properties. It's something called a nuclear orientation thermometer. I'm not sure they use that in this experiment, but usually such systems are used to calibrate this resistor versus temperature calibration, and then you can do that. But strictly speaking, yes, it is a challenge. And in fact, these measurements are very sensitive to lab noise. So your system may actually be at the right temperature, but you will read something incorrect because there is noise in your lab, or there's some grounding issues and things like that. So one has to be careful, but those things are fairly standard and one can do that properly. Okay. So the reason I showed this data is to emphasize that getting this thing to follow this line is experimentally very, very hard. I spent a lot of time doing this and still it never worked perfectly. It was okay for what I was doing for my thesis. So how did the actual experiment prove this? This comes from doing a control experiment, and the hint is related that this quantity, the crossover temperature, depends on this plasma frequency, the small oscillation frequency. And what does the small oscillation frequency depend on? It depends on the critical current and the capacitance, right? Now, for the device, the capacitance is fixed by design, but they could do something where they could change the critical current in situ, okay? So, this is the data from the paper. They call this quantum junction when the critical current is large, and they call this the classical junction when the critical current is small. So, you can see that this I naught here is in this classical junction regime. So, in the range of temperatures we were expecting to do, we were doing the experiment, we did not expect any saturation to happen because of tunneling. So, the black dots is the one which shows this nice transition to a flat region here, and the black arrow represents the crossover temperature using this formula. And the Josephson junctions have this property, because they are made out of superconductors, that if you apply a strong magnetic field, you can actually suppress the critical current. So, in the same experiment, by applying a magnetic field, they were able to reduce the critical current from about 9.5 to about 1.4 microamps, which almost 10 times, which means the frequency went down by about a square root of 10 times, because it's 1 over square root of LC, right? So, what that meant is that if this was saturating due to extra noise, the white data points would have shown saturation exactly at the same point. But as they lowered the critical current, the crossover temperature now shifts somewhere here. So, they do see this temperature, escape temperature going down. It doesn't cross over exactly here, but significantly lower than that one, to convince you that this saturation cannot be due to extra noise, because if that was the case, these numbers would also be up there. Okay. So, this is a very nice example for experimentalists about high quality control experiments you have to do, right? Now, you could have also done this with two different junctions with different critical currents, but that's a separate experiment. It is almost impossible to keep things that identical. So, it was important that they did this in the same experiment with only this extra quantity. Now, of course, one can debate, well, does the magnetic field do something else to the experiment to start worrying about this? But the fact that A, the crossover happens exactly as predicted, and B, that they can show the system is actually cooling down, there is no extra noise, convinces that this has to be due to a tunneling process and nothing else. So, this is why this is a convincing proof, and this was done for the first time, that they showed that a degree of freedom, which is macroscopic because it's a collection of billions of electrons, is showing a tunneling process, and you are seeing that indirectly from these experiments. The second aspect is related to energy quantization, right? That was the second experiment which they did. And so, just pay attention to the top curves here, okay? So, these are the shapes of the potential for different bias currents, like this bias current, and that bias. So, you're slowly going towards the critical current, and the barrier is becoming shallower and shallower. Now, if delta is truly a quantum degree of freedom, then I know that the energy this particle can have cannot be arbitrary. What that means is that when it's sloshing around at the bottom of this well, it cannot have arbitrary energy in it. One has to treat this problem quantum mechanically, which means, well, I have a potential well, I can calculate the quantized energy levels that well supports. That's exactly what they did. So, these are calculations of the quantized energy level which should exist if this was a quantum degree of freedom. And then what they did was they injected an extra signal at 2 gigahertz, so a fixed tone, in order to see how the escape rate changes. Okay. Just step back a little bit. Imagine that this was actually a completely classical scenario, and I'm looking at the escape rate here. If I now inject an additional tone which is resonant with the small frequency of oscillation, that is the resonant frequency of that pendulum at that point, then it's going to put energy into that system. right? Which means it will grow in amplitude, and if it grows in amplitude, it will be easier for it to escape. So if I swept the frequency, I would have seen one frequency at which the escape rate would enhance and then it will come back down, because I'm now adding energy resonantly to this system. They did it slightly indirectly. They fixed the frequency, and again somebody was asking, I'm not sure if because of lack of the right equipment to have a variable frequency source, but they shifted the current. Now because the shape of the potential is changing with the current, the frequency also changes. And what they observe is that for certain values, for a fixed frequency of 2 gigahertz, for certain values of current, they see this sharp enhancement in the escape process. And this they were able to identify with specific transitions. So if you look at this one, which is the biggest one and the sharpest one here, this corresponds to a transition where the ground state is resonant with the first excited state because of that tone there. And that exactly does the same thing. You are able to excite population from 0 to 1. And if you are higher up in the well, it is easier to tunnel. The barrier height becomes effectively smaller and the distance you have to go effectively smaller. But also even through activation, you are sort of up in the well, so you will be able to jump more easily. That's why you see an enhancement in the escape rate. But if this was classical, you would have seen it only at one point. But here you see these different transitions, so, and they could identify this to different transitions. So you observe enhancement to the escape rate under microwave irradiation. The energy levels for a particular current bias can be computed very precisely because you know all the parameters. And then by associating these enhancement peaks with specific transitions, you basically show that these levels must exist. That this phase particle dynamics has to be explained by it living in this quantized energy level picture. Right? So this was the second aspect of this experiment, which is related to the energy quantization. Again, it is related to the phase degree of freedom and hence a macroscopic degree of freedom. Okay, let me see how I'm doing on time. Okay, great. Yeah, so about 10 minutes. I'll finish in 5. I just quickly wanted to show the setup here because some important things had to be developed. This is the sample holder. The chip is here. The Josephson junction they used was actually using niobium as one of the superconductors and lead tin as another superconductor here, lead indium. And the oxide, which was the insulating barrier, was niobium oxide. Nobody makes Josephson junctions like this anymore. Most Josephson junctions these days are made using aluminum oxide, especially for quantum applications. From here to here, where the actual connector is, they have this thing which is a niobium wire, which was used so that when you are passing a large current through this device, you don't heat the experiment. And this is embedded in a copper powder matrix, which is basically suppresses all kinds of high frequency noise. So the filtering environment was very critical in order to ensure that this excess noise does not explain the result. So this was very critical for that, and I think these copper powder filters and all were invented. Now these are all standard techniques which we use. They use this oxygen-free high conductivity copper to ensure good thermalization. This is basically a pure version of copper. And then the microwave signals came from the side and they are weakly coupled to this wire so that you can couple some microwave power for the enhancement experiment.
Copper powder is metallic.
Yes.
So it contaminates superconductivity rather than.
No, so you don't. So it's actually a copper powder in a resin, like a epoxy matrix. But even if you cover, so actually most superconducting wires, if you buy them today, they have a copper cladding on them. So if you're talking about anti-proximity effect, which is suppressing that's a very, very weak effect for something like. In fact, you have to do that to ensure that your niobium wire cools down properly. So you put embedded in a copper matrix. It's also a safety thing that you don't quench the system. So what happens is that when everything is okay, the supercurrent goes through only the superconducting part. The copper part is essentially like a resistor in parallel, but the currents will flow through the short circuit. But they can make a difference if you have time varying currents there. Okay. And this whole thing sits inside a dilution refrigerator, which is a commercial instrument which you can use to cool down to 10 millikelvin typically. So the sample sits at the bottom. There's all kinds of various filters. So they have this microwave filter, then this RF filter, and more microwave filters, and then lots of biasing circuits for the current and the voltage. And the microwave signal also comes through all kinds of attenuation. Again, these are all now standard techniques we use in our experiments to ensure a low noise environment. Many of these things were probably done for the first time in those days to get to the level of low noise you need to do this experiment. This whole experiment was also inside a shielded room, which is like basically a Faraday cage, because just lots of radio frequency noise of various instruments and electrical equipment in the lab can affect this experiment. And I can tell you from personal experience that it is very, very hard to do this. I remember once sitting on one of these kind of chairs, and I was looking at these current distributions, and I would get up and the whole data will go crazy. And I literally lost my mind for about 5 minutes figuring out why is it happening when I'm getting up. Turned out it's a very dry environment in the US. I was doing static discharge every time I would get up, and that discharge would send crazy amounts of RF power into the experiment, and everything would go crazy. So just to give you a sense for what one has to do. So here's a slightly more modern version of that circuit diagram from my thesis, and a picture, because I couldn't find a picture of the actual experimental setup. So here the sample box is here. It's inside a copper box. The whole thing is inside an aluminum box which acts both like a Faraday and a superconducting shield to protect it from magnetic fields from outside, and then various levels of filters and things. In my experiment, I also had to add RF signals for and also listen to them, so that added a challenge. But the reason I did this experiment was actually for the same reason as the control experiment. It was to show that my system was cooling down to a low enough temperature as set by the physical temperature and not due to some extra noise. So I did that as a control experiment during my thesis. Okay. So finally, what is the significance of all of this, right? This experiment basically gave you another quantum object to play around with, which is not atoms and electrons. It showed that electrical circuits under the right conditions can behave quantum mechanically, and that's a huge thing if you think about it. These are things which we can design, make, fabricate, everything is under your control. So this really set the field of making these superconducting oscillators and using them as quantum bits. They're also often referred to as artificial atoms, because unlike nature, where calcium atom is a calcium atom, you cannot do anything about it. If you want a different property, you go to the next atom you have available. Here, I have three elements: the Josephson junction, the linear inductor, and the linear capacitor. And by combining these in clever ways, I have a lot of freedom to construct any arbitrary shape of potential, and hence what kind of quantized energy levels I'm going to have, how it's going to couple to other objects, what are the matrix elements. All of these things are entirely in your hand. And over the years, these different designs gave rise to different kinds of qubits. This is sort of like a periodic table for artificial atoms, where the axes basically are connected to the different values of L, C, and Lj, right? So you have these circuits, they have tunable properties, you can do whatever you want to do with them. You have the ability to manipulate these states with very high fidelity using microwave signal drives. You can also measure the state of these things very, very precisely. And all of this is done using microwaves, which are a lot cheaper, a lot more stable than typically lasers, which you would need for, say, controlling atoms and other such systems. So these technical aspects also played a big role in how quickly this field was able to go from these very early experiments in 1985 to coherent experiments where you could show superposition and entanglement using devices made like this. No one doubts today that electrical circuits can behave quantum mechanically. They are one of the leading platforms. And another aspect here is that by clever design, you can even change the environment. You can design your environment and the kind of noise it sees. So it opens up a lot of experiments, not just in quantum computing. You can also do a lot of interesting fundamental quantum physics experiments, where you can study the interaction of the bath to the system. You can look at quantum measurements in various regimes. And because of the tunable properties, you can really span a wide range of parameter space which is not available as naturally found quantum objects. Okay. And I already mentioned customized Hamiltonians here. So with that, I'll just flash, I've already mentioned this. This is one of the state-of-the-art platforms. We have IBM has announced more than 1,000 qubits, but their better processors have smaller number of qubits. They use a different way of interactions between the qubits, which is they have improved over the years. We have recently heard about Google's 105 qubit, which has shown important contributions to quantum error correction. Prabha here is an expert on, and this is probably one of the more convincing experiments which shows that error correction is sort of going in the right direction, and there is a hope that this would work. And then many other companies like Rigetti, who have made 84 qubits, and China has done that, and our lab is also working on many of these things, including as part of the National Quantum Mission. So I'll just take a few more minutes to sort of end. I was trying to dig up photos from those days, and I realized that smartphones were just starting to come around, so somehow photos are not available that easily. But this is the oldest one I could find. This is from summer of 2004. I think this was at a beach party which we had for the department, and that's a young-looking Michel in 2004. I think he was a little older than I am right now in that picture. So, of course, Michel, I was also his first PhD student at Yale after he moved from France. So that was fantastic because it was a new lab. It was just me and him. His family had not yet moved to the US. So 3-4 hour discussions every other day was very common, which, depending on whom you ask, could be a boon or could be a torture. But it was amazing for a young graduate student at that time and he was always willing to teach. And all these basic concepts of, I did not have any exposure to this field before I joined. And these were the early days of this field. So it was very, very great. And he would give a lot of freedom to come up with their own ideas. In fact, my own PhD emerged from an idea which he had, and later on, during the course of me trying to do the calculations, we realized that there's a better way of doing it, and we shifted to that immediately once I could make a convincing case. I am not in this picture. I am in this picture. This was during my graduation in May 2008. That's me here and here. It was still a relatively small group, about 4 or 5 people. After that, things exploded, and lots of people, huge groups, a lot of money, which happened. But yeah, a lot of great memories of that time. And Michel also visited us in India. So here are some pictures of him in Gateway of India, and then there was a conference in Bangalore. And of course, one has to take a picture in an auto if you come to India. And we even went to some temples during that time. So about John Clark and others, I think, so John was already John Clark was a very senior professor at that time, and probably last few PhD students when I started working with him. Of course, like an expert in squids, that was his main thing. Already at the time in 1985, he was known as the father of squid-based measurements and 1/f flux noise. So got to learn a lot from that experience. The student who was working with me now, is now a very close friend. We talk frequently, and he used to tell me of crazy experiments he did. He was actually trying to do MRI using squids, and they were like doing experiments on actual samples like blood and stuff, and the accidents would happen all the time with cow blood, which could be a problem here, but it was a great experience. And so John Martin is the third person. I had interactions with him both during my early PhD days, but during my postdoc we collaborated on a project, and there's a paper there. But I just want to add that John Martinez was probably the most energetic of all three of them at that time, and was also the one who really wanted to build a quantum computer right from the early days. Now, of course, everyone wants to build them, but he really believed that this technology has a future to get all the way, because when we were starting, it was not known whether these objects would become coherent enough. See, showing quantum effects is one thing, but showing them at a scale which is necessary for technology is a whole other thing. So he always believed, in fact, all three of them are like sort of pioneers of different qubit designs which use different versions. But John Martinez' experiment, the qubit which he initially pioneered, was the closest to this experiment. So he literally used this current bias Josephson junction and the quantized energy levels as the quantum bit to do quantum computing, and a lot of the early results came from that approach. But later on it turned out that if you work with large Josephson junctions, you always have too much noise, and then eventually everything shifted to smaller size Josephson junctions, which was not compatible with that technique. So with that I'll end, and happy to answer any questions. Thank you.
I would like to welcome questions from the audience. So please raise your hands. I'll pass on the mic to you. No, actually I was trying to thank you.
As a single entity, there's just many things happening over time. Yeah. Yes, please.
The next slide,
Yeah.
you showed Clark paper, the one where you excited with microwave.
Yes.
There was a resonant excitation and attributed this to the reduction of the tunnel barrier effectively. Because
more like you are up. Yeah, so you can of course heat up the system by adding additional energy, but only if that energy is dissipated at that temperature. So these experiments are designed, and now of course we take care of even more, that this energy is, if you think about the energy being discontrolled, so most of the power actually just reflects back. The amount of power which is absorbed by the Josephson junction in order to get excited is extremely tiny. Right? It's of the order h bar omega. But the field you send is actually a classical field. So you have this phenomena of Rabi oscillation which causes this excitations to happen. You actually don't absorb too much power, but you need that control field to be large enough to have a decent probability for these changes to take place. But most of that power just reflects and goes back up the chain again and does not dissipate into that. A side point to make is that you see this drive line itself has lots of attenuators. So if you do put too much power, you can actually heat this attenuator and increase the temperature of that. But that will happen at a slower time scale, much slower time scale than the dynamics we are talking about here. But yeah, this were taken care of. And also the fact that it's resonant. Well, okay, I guess you're saying that, so your resonance point was related to the Josephson junction absorbing and hence dissipating.
Can you decouple the barrier effect from the temperature effect, was the thought that was.
So there is no temperature effect because of this. Yeah.
Yeah, just the other where you had I naught, right? Classical and quantum limits, previous one. Yes.
Yeah.
So how did you arrive at that numbers, the 9.4?
Oh, so this number is extracted from this experiment where all of these curves intersect at this point. So you see from this equation, you can show that when I is equal to I naught, this quantity goes to 0. So y-axis being 0 corresponds to the current being the critical current. So this intersection point basically gives you the critical current. So this is another very nice thing about this experiment, that from experimentally measured quantities, you can extract the parameters of the system.
This is for a particular temperature that you are talking about.
No, so you have to do this as a series of temperatures in order to convince yourself that they are all intersecting roughly at the same point. Now, there is an effect that the critical current itself has a very weak dependence on temperature. Okay, but the superconductor here is niobium, whose transition temperature is probably like something in the 5 to 10 Kelvin range, and we are operating below 500 millikelvin. So at these temperatures, the change of critical current will be very, very small. If you did this with aluminum, at 400 millikelvin, you will start seeing the critical current change a little bit.
Okay, that's precisely was my next question.
Yeah.
Which sample was it? It's niobium.
Yes, so this is, I had mentioned that in this, okay, I can, niobium and lead indium on the other side.
Okay, okay. Two different superconductors.
Two different super. Yeah, this was basically because at that time, this was the way they knew how to make Josephson junctions. Yeah, we do them very differently today. Yeah.
Other than electrical circuits, any other macroscopic phenomena you envision, like light matter interaction? Is there anything?
Well, so light, I think again by definition is microscopic because we are talking about photons. Light matter interaction happens in these experiments in modern world. So here the light is microwave frequency. So light is now being used as a generic term for electromagnetic radiation.
Okay.
And matter, instead of being atoms, are these artificial atoms. So light matter interaction happens in exactly the same way you'd expect it to happen for real atoms interacting with light, whereas here it's artificial atoms interacting with microwave frequency light. In fact, there's a corollary name to it. So the original field was called cavity QED. This is given the name circuit QED because this happens at a circuit level. People have, of course, done experiments with macroscopic systems in other ways as well. So, for example, doing Young's double slit experiments using fullerene balls and things like that. They are still probably not as macroscopic as
But
this
they are
one.
not scalable, right?
No, that is, so there are two different things. We're not talking about qubits here. We're just talking about experiments where a macroscopic degree of freedom can show quantum mechanical effects. Scalable is a technical term that, can I make a practical quantum computer out of that? Okay, let me clarify. You don't need macroscopic quantum effects to make a quantum computer. Otherwise, the people in ion traps and cold atoms will be out of a job, or people with photonics. However, I will add a point here that you can consider a quantum computer to be a macroscopic object, right? Prabha, you can correct me. And this was actually a worry in the early days, that we know that quantum mechanics gives way to classical physics, that as we start putting, even if the individual objects were atoms, as we start putting more and more of these together and started creating bigger and bigger entangled state, at some point they will lose all their coherence and become classical. The modern understanding, which also sort of emerges from these early experiments, is that you can still see quantum effects provided you are able to isolate the relevant degree of freedom from its environment. Practically what happens when in a cat or anything much less smaller than that is that this becomes practically impossible to do in many systems or in most systems. But in carefully engineered systems where the number is still under control, you're not going towards infinity, you can still do that in a controlled way and you will retain your quantum effects. It just becomes harder and harder to do it. So people thought that maybe the research into quantum computers may bring about a change in understanding of quantum physics, as if some new mechanism, or maybe we will understand, I don't know, if gravity plays a role, though. All kinds of things have been proposed, right, of why we don't see quantum effects in daily life. So that way one can connect this idea, but as of today, there are no surprises, at least from the point of view of having to rewrite quantum mechanics the way it is done today.
So disintegrated cat works well.
Yeah.
So I just had a question about the idea of a macroscopic phase. So if I think about Cooper pairs as in terms of a 2-electron wave function.
Yeah.
So each of them has an amplitude and a phase associated with the 2-electron wave function.
Right.
So is the macroscopic phase somehow related to the individual phase of each of the Cooper pairs?
No. In fact, the macroscopic phase is a single wave function which is defining the properties of billions of Cooper pairs all acting together. So you can think of this as a Bose-Einstein condensate of Cooper pairs. That's one way of thinking about what is superconducting. So that's the thing. They all work together that the individual identities completely disappear. So the macroscopic wave function is that which is defining the collective properties of all of the Cooper pairs together, not just between 2 electrons and 1 Cooper pair. So Cooper pair, I would not call it as a macroscopic entity. It's just 2 electrons.
I have a question regarding the energy quantization.
Yeah.
So how does the energy quantization for a macroscopic system differ from the kind of quantization you're familiar with for like a single atom?
It does not. That's the whole point of this experiment. You just write the relevant degree of freedom and you quantize. So in fact, Michel Devoret is also known for formally writing down how to quantize electrical circuits, right? So you basically write down the energy, the Hamiltonian, or if you want to write the energy terms of the inductor and the capacitor and the Josephson junction, and then you do the usual thing of promoting those classical variables to a quantum variable, and that's it. So what this is telling you is that as long as even if that variable is interpreted as a macroscopic variable, nothing has to change. You do exactly the same prescription as what matters in the practical terms is that when you have a macroscopic degree of freedom, it becomes difficult to isolate from the environment. So then there are technical challenges on how to do it, but if you understand all the relevant degrees of freedom, you can do that very carefully. So that's the whole point. You don't have to do anything different for macroscopic degree of freedom.
So now we are out of time. So I would now like to invite Professor Sithupati to present the appreciation to our speakers as a gesture of our gratitude.
Thank you. Thank you.
Now let's thank speaker for the time and sharing the quantum wisdom to us.
Thank you. Thank you.